Okay, good evening, everyone. And this is in this live session we will discuss the content related to the week 11. In this, we solved the some examples related to the multi-degree of seismic response of multi-degree of freedom system. In this session, we will solve three questions. Okay, so let us start one by one. So, in the first question, a three-story shear frame is given, which is excited by the horizontal ground motion. Says UZ double dot T. Okay, so we need to determine the generalized solution like the model expansion of the effective earthquake force, the story shear response in terms of the an is the like the spectral acceleration says, and the base overturning moment in terms of the an also. Like if we apply the horizontal ground motion, we need to find the model expansion of the forces, like how the force will be distributed in the modes, and then by using the model expansions we can find out the story shear as well as the overturning moment. So for that multi-degree of freedom system, first work is to calculate the or the finding out the mass matrix, stiffness matrix, and then finding out the what is your eigenvalue, eigenvectors, and then we can start like what the other aspects are asking. Okay, so let us go one by one. First, let us write the mass matrix, which would be the like the this is the first degree of freedom, this is the second degree of freedom, this is a third degree. Same type of question we have solved in the last session. So you can see like how we develop the mass matrix, stiffness matrix, and how we calculate the eigenvalue and eigenvectors. Whole calculation is discussed in this session. So this is a mass matrix. Okay, now come to the stiffness matrix. For this it is given as a like uh, for one column, that is the k is equal to 12 ei by l cube. So for both the story, like there are two columns, so that will be time 2, so that will comes out to be 24 ei by l cube. Okay, so we return as our k is 24 ei by h cube, and like each story has the story same flexure rigidity, so the stereo stiffness is the k and k. So if you will write it as like as we know, k is equal to k1 plus k2 minus k2 0 minus k2 k2 plus k3 minus k3 0 minus k3 and k3. Then you will put like, because k1 k2 k3 all are equal to k, so I got this expression and I taken k as outside, so this will be the my stiffness matrix. Now I will find out the eigenvalue and the eigenvectors. So for this, the equation of the eigenvalue and vector is k minus determinant of the k minus lambda m is equal to 0. So I simplified like uh, I remove or eliminate the m and k terms to is so to make the easy to uh, calculate the to make the calculation easy. Okay, so this is k minus lambda m, and then we after solving the determinant, we got the final equation is this. Okay, so this equation has the three roots. If we will solve this lambda, we will get lambda 1, lambda 2, lambda 3. So these are this lambda 1, lambda 2, and lambda 3. Okay, after getting lambda 1, lambda 2, lambda 3, we can find out what is our mode shifts and what is our natural frequencies. So natural frequencies would be the omega 1 would be the like what will be the natural omega is equal to square root of the lambda. So same for the omega 1, that would be the square root of 0.2679 k by m, and k you know 24 ei by h cube. So from this we have converted this into omega 1, omega 2, omega 3. Okay, after getting the omega 1, omega 2, omega 3, we can get the mode shapes. So from the last question, as I have discussed in the content of the week 10, we have discussed how we determine the mode shape for this the same problem. So from there we have directly get the mode shapes, like for the first mode, for second mode, for third mode. Okay, So now after getting the mode shape, we need to determine the model expansion factor. Model expansion. So do you know what is the model expansion? Model expansion is that, like, if I have a story, and if I have applied a my external force, here the external force is the ground motion. Let us say I applied a force in terms of the, like, the displacement of this story, you can say also, or you can say in terms of the force pattern of the force, like says pt here, pt here, pt here. So my Sn, but the model would be the 111 time pt. So how this is distributed in each mode, like how that will distributed in the, like, this is the 3 degree of freedom, then 3 mode, like for the first mode, for the second mode, for the third mode, how this vector is distributed. Okay, this is the my model expansion. So now in this case I have applied a horizontal ground motion. Okay, in this case, for this story, let us say we have applied a horizontal acceleration. So my Sn would be the m time L. So my influence vector L for this would be the 111 time the 11, because if I apply UG, then here UG, UG it displays by same. So my, so that vector says mass time, and this displacement 1, mass time 1, mass time 1. So how this vector is distributed, like for S1, S2, and S3. So for this we will look into this. Okay, so the model expansion Sn is given as a gamma n m time phi n. So this is the model partition factor, gamma n, mass matrix, this is the mode shape. So first we need to calculate the this vector gamma n. So this gamma n model partition factor, if you have gone through the in the week 11 content or week 10 content, in this they have explained that gamma n given as a phi n transpose time mass matrix time influence vector divided by the phi n transpose matrix time phi n. Okay, so this you can call it as a mn, generalized mass. So for each mode shape, corresponding to each mode, we have one model partition factor. Okay, so here we have three mode shape, so we have three gammas. Okay, so we will go one by one, like how to calculate uh, these things. Okay, so let us go one by one. Okay, so influence vector, as I have discussed, for the horizontal ground motion, the influence vector would be the 111 in the all 3 degree of freedom. So that is the 111 transpose. And the model partition vector, as I have discussed the formulation, gamma n, it is this which I have discussed. So for the, this is the first mode shape, phi 1, this is the mass matrix, this is the influence vector, this is phi 1, this is mass matrix, this is phi 1. If you solve this, you will get it is at a 1.244. Same for gamma 2 and gamma 3. So this way you can calculate your model partition factor. Now after calculating the model partition factor, we can get the model expansion of the vector. Okay, so for this model expansion Sn, that is the uh, gamma n m phi n. So for the S1, S for the n corresponding to one first mode, gamma 1 mass matrix phi 1, So this is the model partition factor gamma 1 which we have calculated in the previous slide. This is the mass matrix. This is the mod shape 1. So corresponding to for the mod 1, this is my mass model expansion, and here m is the mass. Okay, so same for the s2, same for s3. In this we have to need to change the only the gamma 2, gamma 3, and the mass matrix. So, and this total would be the like this Sn would be the like the S1 plus S2 plus S3, and Sn would be the m time L, and m is our mass matrix, m 0 0 0 m 0 0 m by 2 time the L vector 1 1 1. Okay, so if you will do this 3 by 3 3 by 1, you will get a 3 by 1. Okay, so this will be m m by 2. Okay, so your mass, your Sn is distributed like this. If we define on the degree of freedom like this modal expansion for the first vector, first mode shape, and the first corresponding to first degree of freedom, second degree of freedom, third degree of freedom. Same for the mode 2, this is for the first degree of freedom, second, third. Same for the mode 3, first degree of freedom, second, third. Okay, so I have shown in the figure like this is the Sn, overall Sn, which I have calculated here, m by 2, and that is defined and distributed in the three modes overall model expansion in the each mode. So that is the 0.622, like for the first mode 1.073 0.622. For the second mode, if you come out to be, there's a 0.33 for the first mode. For first degree of freedom 0, and that is in the opposite direction because here it is a negative, so that's why it is in the opposite direction. For the same for the mode 3, it is 0.047, then 0.073, and 0.047. So this way. After getting this is the distribution of the mass. You can say also like this is the model expansion of the mass. So if you multiply corresponding to the an, corresponding to the acceleration, your what will your force, from here you can get your equivalent static force, you can get your force corresponding to the each mode. So what is your force, that will be the mass time acceleration. Okay, so if your acceleration corresponding to the first mode is the a1t, for second mode the acceleration would be the a2t, for third mode that would be the a3t. If you will multiply with this a1t, a2, a1t, a1t, so this is becoming your force vector. Force vector in the first mode, force vector in the second mode, force vector in the third mode. So by this we can calculate the shear as well as the moment. Okay, so for this let us go one by one. The story is here in terms of the A and T. So the equivalent static force is given by Fn time SNT, Sn into A and T. So how this is given as a, you can also consider it as Fn we know K time ut, and K time ut is given as a phi vector time gamma n time phi n time dnt. Okay, and K can be written as a omega square time m matrix into gamma n into phi n into dn, and this thing you can be in the discussion the last slide, that is the Sn, and ant is the omega n square time dn. Okay, so that become as a Sn time ant. Okay, this way we have find out this. Okay, f and t. So now after getting f and t, so as I have said earlier, like in the if this is the model mass expansion and multiply this up for the first one, the a1t, a1t, a1t. So this is the forces. So I can get it the my shear force corresponding to. So this is the F31, F21, F11. So do you know how to calculate the shear? For this shear V31 is equal to F31, for V21 that will be the F21 plus F31, for V11 is equal to f31 f21 plus f11. Okay, so this is the v1 v11, like summing all these three, 0.62 plus 1.07 plus 0.62. For the v21, summing only the this f21, this one and this one, and for the v31 only this 0.62. Same for the mode shape 2, mode 2, this is the your f32 f22 f12. Okay, so you can get v32 would be the minus ka f32 because that is in opposite side. v22 would always be like that would be a plus like, but that can be minus 32. Okay, and that would be the f32 plus f22, and for this that would be the f12 f22 f32. Okay, so this way we can get the v12 v22 v32. Okay, similarly you can get for the third mode, in which this is corresponding to f33 f23 f13. So v33 would become as a f33, that would be the f33 plus f23, this would be f13 f23 f33. Okay, and if you do with this addition, then you will get the v13 v23 and v33. So this is the part B, in which we have calculated the shear force in terms of the A and T. Okay, now comes out to the part C, in which we need to calculate the moment. So if you have the equivalent forces, these are the forces, then moment is easily you can calculate. So like after the calculating the shear, you can calculate the combined shear in the first story, second story. So for the combined shear, what will be the combine for the first story? This is the your first story, one 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 in all three stories. So add these for the first story, that would be the v11 v12 v13. For the second story, this one this one this one, so that would be the v21, that would be the v2, that would be the v21 v22 v23, and for the third story top, that would be the v31 v32 and v33. Okay, so this way you can calculate the your stories here in the first story, second story, third story, like we have simply added. Now come to the part C, which is the calculation of the moment, overturning moment. So for this we have written the same type, same figure we have used in the equivalent static forces, which we use in the calculating the base shear. Okay, so in this, if we have the like the equivalent static, so what would be the forces mass, what would be the moment if the height is h h h h h h h h h. So for my mb1 what would be look, so what is this, this is the f31, this is f21, this is f11, this is for mode 2, so that will be f32 f322 f12, and this is f33 f23 f13. So mb1 comes out to be f31 times 3h, this distance, plus f21 times 2h plus f11 time h. Same for the mb2, that would be the f32 times 3h, f22 times 2h, f12 time h. Okay, and same for the this mb3, f33 times 3h, f22 times 2h, f13 time h. Okay, so here the calculation for the mb1, like this is your f31, this is your f21, this is your f11. Okay, and then after solving this you get the mb1. Same for the mb2, like this is your F32, F22, F12 because F22 is 0. Now come to MB3, in which you have this F33, F23, and F13, and this is your MB3. And if you will combine this, so that would be the MB is equal to base overturning move, that would be the MB1, MB2, MB3. Okay, so this way, if you combine this, you will get this expression. So this was the, like, give you the expression that how, once you will be able to calculate the model expansion, then you can calculate easily our base shear, equivalent static forces, base overturning moment. So that will become that will made our things are easier. Okay, so now let us move to the another question. In this, that is the same question whatever I have discussed previously, only the things is changed that I have provided the response spectra. So whenever you are using A and T, you can find out corresponding thing what is the value of A1 here, A2 here, and A3 here. And it's just like replace, you can replace from here. After finding A1, A2, A3, you can find out your values corresponding to this base shear, base moment. But here the one extra thing is also asked, the floor displacement. Okay, and here the combination of the peak is combined with the SRS loop, square root of sum of square. Okay, so this is the same kind of problem in which we will like, as the mass matrix, like the data is given as the height of the story is given 4 meter, mass of the story is given 45,000 kilogram, moment of inertia 58,000 centimeter per, and E is 2 into 10 raised to power 11 Pascal or Newton per meter square. So from the previous problem, question 1, natural frequencies we have calculated earlier. So we have EI value here, we have mass value, we have H, height of the story, and if we put these values like EI and uh, mass and the height for all omega 1, omega 2, omega 3. So I get the omega 1 as a 16.08, and omega 2 is a 43.968, and omega 3 is a 60 radian per second. So after getting omega 1, omega 2, omega 3, I can calculate the time period, or the first the mode shape is given whatever from the last previous question, that is the point 0.5, 0.861. This is mode shape 2, this is mode shape 3. Okay, now I can calculate the time period, which is Tn is equal to 2 pi by omega n. So I will divide, I will get the 2 pi by omega 1, 2 pi by omega 2, 2 pi by omega 3. So this will be my time period. Okay, so coming out to that, T1 is coming given as a 39.07, T2 is 0.1429, and T3 is a zero point 0.1 second. I have calculated like omega 1, omega 2, omega 3 is given, so time period. So for corresponding to this time period T1, T2, T3, I need to calculate my spectral response. So from the response spectra, so can you tell me corresponding to T1, what would be my SA by G? This is your SA by G. Okay, so for T1, 0.390, so that fall into this category, that is around 0.125 to point this 0.66. So your T1 and T2 are falling in this category. Okay, T1 and T2. So your SA by Z 1 is 2.71, SA by Z 2 is also 2.7. Okay, so now, and for T3 is falling in this region. Okay, because time period is from here 0.1 second. So for below 0.1 second, like it is from 0.125 to this one, this range. Okay, so it is below than the 0.125, that is around 0.1046, so that is falling in this region. So for this SA by Z, for that would be the 11.7 Tn time 0.704. Okay, so from this we can calculate the SA by G as a for the first mode, for second mode it is 2.7, for third mode that is the 11.7 time Tn raised to power 0.704. If you will put the Tn is equal to T3, that is 0.106, so that is coming out to be 2.387. Okay, so from multiply this with the G SA, that is become 26, SA2, SA3, and here that is given your response spectrum is equal to 0.20. So if I scaled it to point multiply with the point 2, I will get my spectral acceleration. So the design spectrum is scaled by 0.2g, that is given in the question itself if you will read it properly. So that a and t become as a zero point 0.2 time SA n. So the acceleration a1 is given as a multiply it with the point 0.2, multiply it with the point 0.2, multiply it with the point 0.2. Okay, so a1 is given as a 5.317, a2 is 5.317, a3 is a 4.684. Okay, so this is your acceleration. So now we need to calculate the displacement. Okay, so for the displacement we need to calculate the first displacement d. So what is your displacement? D is equal to a divided by omega square, omega n square. So for d1 that is a n divided by omega 1 square, so that is the for d1 it is coming out 0.020 meter, d2 0.0275 meter, d3 0.00129. Okay, so after getting the d1, d2, d3, we can get the first, we need to also the model partition factor to calculate the response, to calculate that was the model response na, d1, d2, d3. Now we need to calculate the over u1, u2 displacement in each mode. Okay, so the from the previous question model partition factor for the 5 gamma 1, gamma 2, gamma 2 and gamma 3 is given here as we have calculated in the question 1. So after calculating the gamma 1, gamma 2, gamma 3, we can get the Q1 model response. So that will be the gamma n time the Dn. Okay. So if we calculate it, it will become as a Q1 is equal to gamma 1 Dn. So that gamma is 1.244 and that is the D1. So that become as a 0.0255 for the Q2 and Q3. Now after getting the this model response, now we can calculate the flow displacement. So that is the flow displacement is given as a u1 t is equal to phi n time the q1. So for the first mode that is the phi 1 time q1. So that will gives us a u11, u21, u3. For the second mode phi 2 u2, that will give us a u21, u12, u22, u32. For the third mode phi 3 q3, that would be the u13, u23, u33. Okay, so this way you can calculate your u1, u2, u3. So for the u1, this one, and phi 1 multiply this is your phi 1 vector and this is your q1. So if you will calculate and multiply it with 1000 also to convert it into mm, so that is your u1 12.75, 22.08, 25.5. Same for the u2t, so that is the pi 2 times the q2. So if you will multiply this you will get minus 0.915, 0.915. Same you can get it for the u3. Okay, so you get the displacement of the degree of freedom corresponding to each bonds. Okay, so now the total displacement for the first story, that would be the u1, u12, u13, like corresponding, this is corresponding to the mode in all three mode for the first story 111. Okay, so that is coming out to be 11.88 for the second story and for the third story. Okay, now come to the stories here. So for the stories here we have discussed as we can calculate as a fs is equal to k time un, that is omega n square m time un, or if we can do it by fs k un and simplifying this is as a model expansion time a1. So we have calculated the model expansion earlier, so from this we can calculate directly, we can use it here. So this vector, this is from the previous question. like this model expansion, and put the value of the mass as a 45,000 and A1 as a 5.31 something or 5.7 something. Okay, whatever it is. So you will get your F31, F32, F21, F11. Okay, same for the second mode, that is your F32, F22, F12. From this is F33, F23, F13. Okay, so after getting these static forces, you can calculate your you can calculate your uh, storage here directly by V31 is the F31, V2 is the F21 plus F31, and V1 is the F11, F21, F31. Same for V32, that will be the F32. For this V2, that is the F22 plus F32. For F11, that is the F12, F22, F32. Okay, and for this V33, that is the F33, V23, that is the F23, 223, F33. For V13, that is the F33, F21, and F123. Okay, so this way you can calculate your storage here corresponding to each mode. Okay, this is corresponding to the first mode, this is corresponding to the second mode, this is corresponding to the third mode. Okay, now coming to the moment, so same we have done in the last question. Same way you can calculate the moment also, like this is whatever the forces, like this is the F31, F21, and that would be our MF11. So here the moment would be our M31, here a moment would be M21, here our moment would be the M11. So M31 is coming out to be multiply F31 time H, which is 4, F21 coming out to be F31 time 4, or H plus 2H, that would be 2H plus F21 time H. For this, that will come as a F11 time H plus F21 time 2H plus F31 time 3H. Okay, so if you will put the F force value, F3 or F21 or F1, and H value, you will be able to find the moment. M11, M, so your M11 is this one, is calculated this F11H, F21 into 2H, F31 into 3H. Okay, so this way we will get our moment as a 4435.57 kilonewton meter. Same way M21, same way M31. Okay, so after getting the moment for the first mode, now same you can get the overturning moment for the second mode. So for this M12, like this will be our M32, this will be our M22, this will be our M12. Okay, so M12 is coming out to be this one, this is our F32, this is our F22, this is our F12. Okay, so if you will put the values, F12, F22 is 0, F32 is this 39, so you will get your M12. Okay, same M22, same M32 you can calculate. Similarly for the third one, that is your F33, F23, F13, and your this moment is the M33, M23, and M13. Okay, so you can calculate the M13, M23, and M33 here is. Okay, so this way you can calculate the overturning moments. Now we comes out to a part B, in which we need to calculate our peak responses by combining the SRSS model. So the peak response by SRSS, so the first floor, the floor displacement is can be calculated for the first floor, that is the square root of the sum of square, so that is the U11 u12 u13 square root of this. So you can get the, like we have given the vector of the u1 u2 u3. We have calculated it. These are the things in the part A. So u1 for the second floor same, u21 square, u22 square, u23 square. So this is our u2, and for third floor you will get this one 25. Okay, so in the previous one that is given as a u11 u21 u31 u12 u22 u32 u31 u23, sorry, u13 u23. So this is the peak displacement, that is 12.78 for the first story. For second story that is will be the 22.08, and for third story that is the 25.5. Similarly, you can find out the stories here. For the first floor, that is the V1, V11 square plus V12 square plus V13 square. So you can calculate the V11, V12, V13 by putting the stories here. Okay, like we have calculated those now. V11, V21, V31, and V12, V22, V32, and V13, V23, V33. So for the first story, for second, and for third. Okay, so this way you can calculate the stories here. Like we have calculated the stories here already, but you need to calculate the in the you need to calculate only the combined peak responses. Okay, so uh, V1 is the 555 kilonewton, V2 is the 407, and V3 is the 154 kilonewton. Same for the overturning moment. So we have calculated all these quantities. So you can perform the same type of calculation here, which we have calculated in the earlier for the shear and the displacement. So these are our base moment for the first floor, for second floor, for the third floor. This way you can do it. Okay. So for this M1, M2, M3. Okay. No, sorry, that would be the M3, M2, and M2. Okay. So this is your overturning moment. Now this is the same kind of question we are doing in this the last question of this session, in which we are using an inverted L type structure, in which we need to calculate the same, like we need to calculate the bending moment and the displacement mainly. So for this, like this mass matrix and the flexibility matrix we have calculated in the week 8 content. If you will go in the week 8 content, question number 4, you will find that we have calculated the flexibility matrix. So if you go through flexibility, if you know the flexibility matrix, then you can calculate the stiffness matrix, that will be the inverse of the flexibility matrix. Okay, stiffness matrix is the inverse of the flexibility matrix, and the mass matrix we have calculated here. So after getting the mass matrix and the flexibility matrix, we can calculate the our mode shape, um, uh, uh, model frequencies, and then we can find out the load vector. So here one thing, our ground motion is given this way, inclined, not the horizontal. Okay, so I will ask one question after when we reach the determining a load vector part. So first we let us calculate the properties of this these, like the model mass and all these stuffs. Okay, so let us come. So the mass matrix, so if you will give the unit acceleration through this, so that will be moved by one acceleration unit, that is one. So that for the m11, that will become as a m plus 2m, and all else other will be 0, so that will be 3m. If you will give the unit acceleration to this one, so only this one will move, this will not. Okay, so that m22 will be the m, and all other would be the 0. So that is our mass matrix. And for the flexibility stiffness matrix, I have told you that from the week 8 live session, question 4, if we will go, we have calculated the flexibility matrix. So if you know the flexibility matrix, you can calculate the stiffness matrix as a inverse of this. So I have taken the inverse of this, and this is my stiffness matrix, that is the 6 EI by 7 L cube, 8 minus 3 minus 3 2. Okay. So after getting this, and here I have written 6 pi by 7 l cube as a k dash. So that is the 6 pi by 7 l cube, and if I have put the value of ei and l, I get a k dash value. So from this k and m, I can calculate the eigenvalue and the eigenvector. So that is coming out to be this one. So this equation, I got this for the eigenvector, and then if I will solve this eigenvalue, I will get the lambda 1 is equal to 0.57 k dash by m, and lambda 2 is the 4.07 k dash by m. Okay, so the omega 1 is the 10.19, and the omega 2 is the 27.14. Okay, radian per second. So from here, also with the using this, I can find out the mode shift 1, 2.0971 minus 1.431. So using this, we can also find the time period also. But here the first is the influence vector. So like this is a mass m, this is a mass 2m, and this is this is l and l. If I apply a horizontal ground motion UZ double dot, so and my u1 is this and u2 is this, so my u1 will move with the uz double dot, but my u2 will not move. So my influence vector would be the 1 0. Okay, if I apply the vertical ground motion downward uz double dot, then my influence vector would be the 0 and 1, because the other degree of freedom will not go into this direction. In this u2 is the displacement or the acceleration in that direction will be 0. Now I have provided the ground motion acceleration direction into this uz double dot. So this is the this like this content. So if I will divide it into the content, like into the component, so that is the obviously that is same height in the length. So that will be the 45. So that will component will be the ug double dot by 1 by root 2, and ug double dot by 1 by root 2. So that for u1, but this component in the upper direction, but my direction of the degree of freedom is in the lower direction, u2 in this direction. So that would be the negative. So my p effective would be mass matrix time ug double dot under root 2 and minus ug double dot under root 2. So if I will write it m time uz taken outside uz and taken as a l influence vector, that is 1 by root 2 minus 1 by root 2. So this is called as it as a l. So that will come as a m uz and l. Okay, so this l influence vector for this particular case is the 1 by root 2 minus 1 by 2. Okay, so here I have also like solved this way, like giving this and then divided it into the component component. So or obviously my degree of freedoms are this and this. So this one is this in the same direction, but this one is the opposite direction. Okay, so that's why my influence vector, this is the negative sign in this, because my u2 is in the opposite direction. So this is the influence vector. So now using this influence vector, we can calculate the model expansion, or with the model expansion we can get the our solution of the uh, we can get our solution corresponding to the bending moment, shear force, or anything else. So first we need to find out the displacement. Okay, so part B, for this time period we need to calculate, as we have calculated the omega 1 and omega 2, time period can be 2 pi by omega n. Okay, so T and T2 we have calculated time period, So corresponding to this T1 and T2 from the response spectra, for the T1 is a 0.62, so that is into this range for T1. So that would be SA, so that SA by Z time 1, that would be zero point 0.5 divided by 0.62, and the T2 is the 0.23, so that would be into this region, so that would be the 1. Okay, so SA by Z, that is the zero point 0.5 by Tn, and the that is coming out to be 0.805, and SA by Z2, that is 1. If I multiply it with the Z, so that is 7.9, and that is 9.81. So this is my A1 and A2. So after calculating the A1, A2, I can calculate the displacement. Okay, so displacement is given as a dn is equal to an divided by omega n square. So omega n I know in the from the uh, that was the omega 1 was the 10.19, on omega 2 some 14, I don't remember the 14, and omega, let us find out what was the 10.19, and that was the 27.14. Okay, so this way you can calculate your d1 d2, that is coming out to 0.07714, and that is coming out 0.0133. Okay, d1 d2. So after getting d1 d2, you can first need to find out the modal partition factor. So for this, gamma 1 is the phi 1 transverse mass matrix L, phi 1t m phi 1t. So this is the phi 1 which I have calculated. This is mass matrix, and this is my influence factor L. And this also the negative sign should be there. Okay, so phi 1 mass matrix phi 1. So I have calculated that. So that is coming out to 0.0865. Okay, gamma 1. Same for the gamma 2. So this is also negative sign is here, but that is not visible actually. Okay, so phi minus, and if you will put the phi 2 mass matrix L, you will get the gamma 2. And actually you should remember like that gamma 1 plus gamma 2 should be equal to 1. Okay, but here that is some 0.08, that 0.62, so that is equal to, because the L is your 1 by root 2 something. Okay, so that's why it is coming out to be some 0.702 something. Okay, so that's why it is coming to not that one. If your that was the horizontal ground motion, that was UZ. And if that one, if you will look into the previous questions, and if you will summing of the gamma 1 gamma 2 gamma 3, you will find your total sum of the factors would be the 1, because that is the horizontal ground motion. Your influence factor was 111. Okay, so after getting gamma 1, gamma 2, you can find out the Q1, that is the gamma 1 dn. So for this Q1 gamma 1 dn, gamma 1 is given, dn is this, they have calculated. So that is a Q1 is the 6.67 mm. Okay, same for the gamma Q2. So that is the gamma 2 d2, so that is coming out to be 8.25 mm. So after getting this, you can calculate the flow displacement, that is the UNT, that is the phi n and Q1, and phi n is this. Uh, so for this U1, that is a U11, U21, so that is phi 1, Q1, 1, 2.097, that is phi 1, and that is the Q1. So this is the displacement 6.67, 13.98 mm. U1T. Same for the U2T, that is the U1T, 2, U22. Okay, so phi 2, U2. So this is the phi 2, and this is the displacement 8.25, and this is the coming out to you. So now to combine peak response by the SRSS. So for the first, that was the first U1 and U2. Okay, so U1 would be the U11 square plus U12 square, and U2 would be, sorry, that would be U21, U12 in the second game. For this U2, that would be U21 square plus U22 square. Okay, so the peak response for U1 is given as a 6.67, 8.25, that is 10.6 mm square, and for U2, U21 square plus U22 square and the square root of both, that is the 18.49. So these are the peak responses. Now coming out to be part C, in which we need to calculate the bending moment. Okay, so the for the bending moment, as we have if we calculate the here the model expansion, we can do this. or we have the displacement. Okay, so one way to calculate this uh, via model expansion, and one way to calculate the fn with time the k into u, or k time uh, k can be replaced as a m matrix omega n square, and u can be replaced as a uh, and u we know actually, u vector we know. Okay, or you can replace it with the u as a, you can replace u as a gamma n time phi and time q1 qn. Okay, so corresponding to each vector you can calculate by this, or you can calculate this by the model expansion vector. Okay, that depends on you. So here we are going with the model expansion. So Sn, so Sn S1 we can gamma 1 we have 0.08865 mass matrix 3001 m, and the phi 1 this is 0.2595 0.1814, and model expansion 2 same for the S2, that is a gamma 2 m pi 2, so that is coming out to be 0.6204 3001 mass, that is a phi 2, and that is coming out to this. So now this can be written in the shown in the figure. So the equivalent static force, that is coming out to Fs times the An, like this is the mass actually, no? If you will multiply mass with the acceleration, will give you the force, mass time acceleration. So that is Sn into An. So if you will show into the figures, so that is your corresponding to 1, and that is downward 2. So for the mode shape 1, that is your mass is a1t. Okay, and for the second, that is a a2t. So that is 0.2595. I have round of it is as a 0.26. If I multiply this the a1t, that is become as a 0.26, and if I multiply this 0.184 time a1t, so that is this. Okay, this is the expansion of the force, this is the one force. Now for the second mode, that is the 1.86 multiply time the a2t. Okay, so that is 1.8612 time m into a2t, and this is the negative direction time a2t, this is in the opposite, in the upper direction 0.887 mm. So from here you can directly calculate your bending moment. Okay, so for calculating the bending moment, for this is given to you 3 meter actually. Okay, so that you will calculate if this is what for the first one, that is f11, that is f21. Okay, this is was f12, f22. So mb1 would be f11 time 3 plus f21 time 3. Same for mb2, that would be the f12 time 3, but that f22 in the upper direction, so that moment would be the f22 into 3. So this is the mb1 mb2. Okay, so from this mb1, that is you will calculate 0.26 m a1t time l is the 1, and 0.81 m time, so that is coming out to be 0.4414 m into m a1l. So m is given to you some 75,000. Okay, and the a1 we have calculated as a 7.9, and l is 3 meter. So if you will do the calculation, you will get into the newton meter, and if you will convert it into the kilonewton divided by the 1000, you will find out 784.58 kilonewton. Same for the mb2, whatever I have written 1.86 ma2, like f12 is a 1.86 ma2 into l, minus that I have written here f22, this is a 0.887 m into a2, that is this. And if you will put the values of m, l, and we have calculated that was the 9.81. Okay, so that is coming out to be this, so that is 22,150 150.3 kilonewton meter. So the peak response can be calculated as MB is equal to MB1 square MB2 square. So that is MB is the this 784.58 square plus 2150 that is we are getting the 22.2289 kilonewton meter. So that is the overturning moment for the this inverted type L type structure with this mass here, this is mass here, U1 and U2. Okay, so that is okay. That's all for this week. If you have any doubt or uh, any doubt, and if you have any questions related to the assignment solution, you can ask me here, or you can ask me through the Google form or the Google form discussion form from the NPTEL portal, or you can ask me through the comment in the videos also. I will give you the answers. Okay, so if you have any doubt, you can come to me. Okay, so I am ending this session. Thank you.